This video demonstrates the Simulation Solutions Generic Distillation Simulator, which consists of a digital control system with 6 unique schematics, as well as a 3D virtual reality outside operator. Like all Simulation Solutions modules, these two programs are two-way communicable, such that any change made on the DCS will also be shown on the outside operator, and of course vice versa. This distillation column is a binary separation between two hydrocarbons, in this case pentane and hexane. This hydrocarbon feed enters the tower under flow control, and when a level builds in the tower, a level controller determines the amount of liquid flow leaving out of the bottom stream. Temperature is controlled with a thermosiphon reboiler, which emits a steam flow to heat the liquid level sitting at the bottom of the tower. This heat then sends vapor product overhead in the tower, which then is condensed into a reflux drum. The liquid in the reflux drum can then either be sent back down the tower as reflux flow or leave the system as the overhead distillate product. As a note, this distillate product is controlled by the reflux drum level controller, while the reflux flow is controlled by a reflux flow controller, which can be cascaded to the temperature at the top of the tower. You can also note that in order to save energy, the bottoms product stream has been designed such that it is used to preheat the feed flow before it enters the column. Flow rates of both distillate and bottoms product streams and their compositions are displayed via indicators throughout the column apparatus. Moving to the next schematic, we see a more detailed view of the distillation column itself. Trainees can note both the temperature and composition at each tray of the tower. These readings allow trainees to see in more detail how changing the temperature, pressure, or flow rates leading to the tower ultimately affect the hydrocarbon separation. So now I will demonstrate by changing the flow rate into the tower, and we will see how the composition and temperature profiles adjust. So now I will put the output of the controller into 55%, open, and we will see how the composition changes. So you see the temperature is decreasing, the composition is changing in each respective stage. Even if it's a slight bit, it's still a change. The temperature profile will adjust as well, and it will change accordingly to account for this change in flow rate into the tower. On the next schematic, we see the distillation overhead is shown in more detail. It can be noted that the cooling water to condense the overhead vapor is on straight flow control, and the pressure controller for the system makes use of a split range control scheme, which either bypasses the condenser to build pressure or relieves pressure through a vent. Next, we will focus on the bottom of the column, where trainees can see more details regarding the thermosiphon reboiler that was previously mentioned. If we recall, this thermosiphon reboiler helps control temperature and emits a steam flow to heat the liquid level sitting at the bottom of the tower. That heat is then sent overhead in the tower and is condensed in the reflux drum. The fifth schematic of this distillation simulator includes a dynamic profitability analysis spreadsheet, which calculates the costs and profits of running the distillation process. You will see in the top half of the spreadsheet, trainees will have costs, which include column feed and reboiler steam, as well as penalties for off-spec products. When running the simulator, we would expect the use of steam to be low because it can become very expensive and not economically favorable. Meanwhile, the bottom half of the spreadsheet calculates the credits or earnings for running the column, and this includes for the bottoms product and the overhead distillate product. It is important to note that the overall profitability of the plan is calculated dynamically and done so from both an instantaneous profit as well as an accumulated profit standpoint. The final schematic of this program is a stripped-down version of the overview schematic of the column, which was the first schematic shown. This schematic is the optimization schematic. Here, trainees can view the feed entering the system, the product streams and their compositions, as well as the profit numbers. When completing startups and/or optimization exercises, trainees can keep track of the main drivers of the process, as well as enhance their understanding of the foundations of the distillation process. So now we will move on to the 3D virtual reality outside operator, and I will demonstrate what would happen if the outside operator closed the cooling water block valve in the field. On the DCS screen, HS126 controls the cooling water flow. Here is the 3D virtual reality outside operator, and now we will find the hand switch that controls the cooling water. So we have found hand switch 126, which controls the cooling water. So now if the outside operator were to shut this block valve, we would see that the switch becomes red, indicating that it is closed, and we hear beeping, and we see that there is red flashing. So this indicates that an alarm is going off because something is wrong. In this case, cooling water is being lost in the process, and the process is unable to adjust to this lack of cooling water because the process needs cooling water. But that two-way communication that you saw between the DCS screen as well as the 3D virtual reality outside operator is true for any piece of equipment in this distillation program. So for example, if I were to make the same change on the DCS screen by closing this, we would have the same result on the outside operator. For more information on the distillation program or any other Simulation Solutions products, please call 732-389-5400 or go online to www.simulationsolutions.com.